Good afternoon. This is my presentation for SmallSat Conference SSC 20-IX-01. I'm Professor Stephen A. Whitmore from the Department of Mechanical and Aerospace Engineering at Utah State, and my presentation is entitled Nytrox is a volumetrically efficient green oxidizer for SmallSat hybrid propulsion systems. Basically, the bottom line is that why develop green propellants for in-space propulsion? Well, bottom line is that hydrazine, with all of the associated environmental hazards, toxicity, the ability to manage the associated servicing and storage requirements with hydrazine have gotten to where it's just become environmentally unsustainable and it's just too expensive. So there is an emerging need for alternatives to hydrazine, and USU has been developing a hybrid alternative to hydrazine for about 10 years now, and we've had quite a bit of good success. So we're building on that for this particular paper. Essentially, what we've done is we've exploited the emergence of additive manufacturing to help develop a green hybrid. The biggest issue with hybrids up to this point, hybrids being some kind of inert solid fuel and in a separate gaseous or liquid oxidizer, the biggest issue is the hybrids at this point is there had never really been a good method by which you could do reliable in-space start and restart on demand. And one of the things that we learned by looking at the characteristics of certain 3D printed materials, ABS being chief among those, is that in the process of 3D printing, it changes the dielectric properties. So if these materials are hit with an inductive charge corresponding in addition to a flow of an oxidizer, you basically get a scenario where joule heating causes an immediate on-demand ignition. And the number of ignitions is only limited by the amount of fuel that's in the system. One of the nice things about this is that it is a very inexpensive mid-level technology, and we have developed this to a fairly high level of TRL readiness. We've gotten quite a bit of experience at this point with gaseous oxygen and peroxide. We've also had some success with nitrous oxide. The advantage you can see with this is it scales over a wide range. You can crank out a bunch of stuff, and you don't need a very large print section because you can print these in segments with even a small printer in the size of an ES1200 dimension. You can still print some fairly substantial size fuel materials for this. So we actually flew a prototype 10 Newton thruster of this system out of NASA Wallops. Back in March 2018, we flew above the von Karman line and were able to get 5 restarts in space. So we do have a little bit of spaceflight heritage on this system. Basically, there's an overview of the project where we basically flew suborbital. We did get enough time above the von Karman line. You can see the packaging of the system into the flight deck that went into the Terra Malamute, and we were able to get a very successful test. The biggest problem up to this point is that the highest TRL uses gaseous oxygen as the oxidizer. GOX is a really good oxidizer to work with in that it's very, very friendly, and the processes for GOX cleanliness are very well established, and it's a very safe and reliable oxidizer. The biggest problem is it's not very dense, and so it's very volumetrically inefficient. So we started out this project looking to replace it with some other options that had higher density. And really, if you look at green oxidizers for hybrids, you can see down here with this box with the dashed line, there are really only four alternatives: liquid oxygen, gaseous oxygen, nitrous oxide, and hydrogen peroxide. Well, it turns out that LOX is not a good space propellant, basically because it's not storable. Hydrogen peroxide has been proposed as an in-space propellant, but extensive experience of working with hydrogen peroxide at Utah State has shown that it's not a good space propellant. It doesn't do well at cold temperatures. You have issues with catalyst beds ineffectiveness, with peroxide pooling. We've actually blown up several rockets using hydrogen peroxide under cold temperatures. We wouldn't recommend it. So really, you're left with two: gaseous oxygen and nitrous oxide. The big issue with nitrous oxide is that it does have a very energetic decomposition reaction, and that energetic decomposition reaction is actually potentially dangerous. However, if you blend the two of them, this is just the properties that you could pull out of the paper. If you blend the two of these, you can mitigate the effect of this decomposition reaction, because in the process of blending nitrous oxide and oxygen together is that you replace the ullage, which is normally vaporized nitrous oxide. That a lot of that ullage gets replaced with a solution of nitrous oxide and oxygen, and having that nitrous oxide or the oxygen in the ullage, oxygen doesn't have a decomposition reaction, actually does a lot to mitigate that. As a matter of fact, if you have just even at fairly low oxygen concentrations of around 20%, you can see that basically about 4,000 reduction in the risk, or 4,000 times more energy to cause that decomposition reaction. It turns out that at 0 degrees C, if you store this over ice, that if you percolate this system so that you reach a vapor at saturation vapor pressure at around 1,300 psi, you get a maximum concentration of oxygen in the ullage, while only getting a moderate concentration of oxygen in the liquid component. And your liquid density only reduces from about 900 kilograms per cubic meter down to about 790. So not a huge reduction in density, but a huge reduction in the overall risk of using the system. You can see performance. There is a small hit in performance in terms of specific impulse, but by the same token, your volumetric impulse actually goes way up, and your volumetric impulse using Nytrox, an 87% solution of nitrous oxide and ABS as propellants, is basically about a factor of 10 greater than if you use gaseous oxygen and ABS. So we built a legacy system. This legacy system, or we leveraged a legacy system that had been previously flown on the 10 thruster that had been previously flown on the spaceflight test. We took that system and we reconfigured it so we could drop in nitrous oxide or Nytrox, basically an 87% solution of nitrous oxide and oxygen as a replacement. And we did a series of evaluation tests. What we found when we dropped this in is our performance was almost identical. Ignition energies were very close to the same. You can see we had a slight introduction of latency into the system due to the fact that we had to vaporize it. This is because we were using a single port injector. I think if we used an atomizing injector, that latency would go away. You can see when we compare the performances of the two systems, on this column is the GOX ABS baseline. On this column is the Nytrox ABS. And you can see that comparing performances, that everything is almost identical. Slight increase in specific impulse when you compare GOX to Nytrox. And it's because nitrous oxide is not quite as good of a oxidizer. You had a little bit of an increase in thrust on the system, and that's because of the higher density of the Nytrox. Mechanically, they behaved almost the same. The C sub F was the same. We look at the actual equivalence ratio and the achieved O to F ratios. You can see that both of these tend to run just a little bit fuel rich, which was good. That reduces any potential for an erosion. And you can see applying the regression rates, we are not quite as good as if we were using gaseous oxygen and ABS, but we're significantly superior to the other propellants like LOX and nitrous oxide by itself. So you do get some increased performance and regression. When this system is actually extrapolated, the performance of the Nytrox ABS is extrapolated out to vacuum conditions. You can see that we achieve almost 300 seconds of ISP, which is actually quite good. And then the big factor here is when we go through our comparisons, and I wanted to go back and look at that. When we go through our comparisons for the nitrous oxide compared to some of the existing space propellants that are out there, you can see when we look at this system, is that we operate at a significantly higher flame temperature than the monopropellants. You can see that we operate basically a factor of 3 higher flame temperature than the hydrazine, because we do have truly a bipropellant system. And then if you look at LMP103S and AFM315E, which are the ionic liquid propellants, we're about 1/3 higher. Now, at first glance, it would seem that higher flame temperature would be a problem, but remember, because ABS has this energy of ablation, is that pyrolysis layer at the surface tends to act as an insulating film, and the printed plastic material by itself has a very low thermal conductivity. So these motors tend to not get hot. The ionic liquid propellants, when you look at the thrust chambers on there, they glow white hot, and basically after even as much as 30 seconds of burn time on our Nytrox ABS system, is that we barely got above 400 degrees C for the external chamber temperatures on this. And after very short burns, the kind of you would have for pulse burn for a small spacecraft, you can almost put your hand on it after you end up with your burning. Basically delivered ISP pushing around 300 seconds, which is considerably better than both the ionic liquid propellants, and certainly much better than hydrazine. Our specific gravity, when you look at the combinations, a little bit lower. We're about a specific gravity of about 0.65 to 0.7. When you compare that to the specific gravity of the ionic liquid propellants, it's a little bit lower. But when you consider that hydrazine and the ionic liquid propellants all need a top pressurant system, these are not self-pressurizing propellants, whereas the Nytrox is a self-pressurizing propellant. Because Nytrox is a self-pressurizing propellant, is that we don't need all that separate system. So in terms of the actual dry mass associated to support the system, we are actually quite a bit better. And so this density impulse comparison is actually a little bit misleading. We obviously knock hydrazine way out of the water. We're a little bit lower than the density impulses you would get out of LMP and AFM, but because we don't carry the separate system, we're actually more volumetrically efficient. One of the big ones to keep in mind is the fact that all 3 of these traditional propellants, hydrazine and the 2 ionic liquid propellants, require a substantial preheat, as much as 15,000 to 20,000 joules of preheat, whereas our system requires no preheat at all, and a single ignition cycle only takes about 4 to 10 watts for 700 milliseconds. So a complete ignition cycle takes about 2 to 5 joules, which is essentially negligible. The ionic liquid propellants have a really difficult time working when you get, and hydrogen, when you get to very cold temperatures. You do have to do some kind of propellant maintenance to keep these things from freezing up. And it turns out, though, that Nytrox actually performs better the colder it gets. You get a much denser system. You get more oxygen and concentration in the liquid. And so Nytrox has been tested to as low as minus 70 degrees C now. And we have had no problem at all. The Nytrox system actually performs really well. If you look at the cost is marginal compared to the ionic liquid propellants. These things are limited access. They're very restricted to get a hold of. And obviously, these are very widely propellant. ABS is the most common 3D printable material. And nitrous oxide you can pretty much get from any of the major gas distributors. The big one is obviously, if you look at the payback on this, there is absolutely zero, it's inflammable propellants, zero associated toxicity risk. It is a fairly strong, nitrous oxide is a strong oxidizer, but if oxygen standard cleanliness is handled, no problem at all. So you can see that the cool thing about this is we can print up, because of the 3D printing, a myriad of configurations. And you can see we're investigating a whole bunch of different options on this. So we really feel like we have a market disruptive technology here. The big one is that when we dropped it in, it worked. And we feel that by pressing on with nitrous oxide that we are going to have a really good replacement for nitrous oxide and 300 second space ISP. Thank you. I appreciate